Dr. Krishnanand Kaipa. So, Dr. Kaipa is a tenured associate professor in Department of Mechanical and Aerospace Engineering at Old Dominion University. Dr. Kaipa received his BE in Electrical Engineering from Birla Institute of Technology and Science, Pilani, and his master and PhD degree from Indian Institute of Science, Bangalore. He pursued postdoctoral studies at University of Vermont and University of Maryland, where he was also a research associate professor. Dr. Kaipa directs the Collaborative Robotics and Adaptive Machines laboratory, which aims to make fundamental advances in science and engineering of robotics with a diverse application in autonomous systems, advanced manufacturing, and healthcare. His research has received federal funding from National Science Foundation and Office of Naval Research. He has published one book and more than hundreds paper in journals, book chapters, and referred conferences proceedings, and has been awarded one US patent. He received the Best Master's Thesis and Best PhD Dissertations Award, Best Paper Awards in International Conferences, Outstanding Book Chapter Award, and an Outstanding Teaching Award for a graduate course at UMD. Dr. Kaipa currently serves as an Associate Editor for IEEE Robotics and Automation Letters, IEEE Conference on Robotics and Automation, and ASME Journal of Computing and Information Science in Engineering. He serves as a conference chair for ASME 2025 Computers and Information Engineering Conference. With that, I now invite Dr. Kaipa to begin his presentation.
Yeah. You're able to hear me, correct?
Yes, sir. You can share the slides.
Thank you, Abhijit, for that nice introduction. Good afternoon, everyone.
Professor, we can't see the slides.
Yes. Yeah, let me share my screen. I'll have to share sound too, correct? Include sound. Okay, yeah. Good afternoon, everyone. I'm Krishnanand Kaipa, Associate Professor in the Department of Mechanical and Aerospace Engineering at Old Dominion University, located in Norfolk, Virginia. Let me begin by saying that I'm deeply honored for making the presentation today at Assets 2025 on the account of felicitation organized for Dr. Debasish Ghosh. I'm really missing not being in person. And my journey with Ghosh sir started, I think, 2002, doing masters in multi-robot formations, and then continued into a PhD with sir. And as part of PhD, we developed a novel swarm optimization algorithm, glowworm swarm optimization, which has diverse applications ranging from optimization all the way to robotics. And we eventually wrote a book on that topic. So whatever today, I'm immensely indebted to sir in terms of my professional career and also in general as a guidance in general in my life. Okay, so today's talk is focused on some of the recent work we did on the topic of in my lab on the topic of autonomous robotic floats for applications in oceanic observation. To give some background, autonomous underwater vehicles have diverse applications ranging from deep sea, littoral to estuary environments, such as marine biology exploration, ocean environment monitoring, search for plane crash sites, pipeline and ship hull inspection tasks. AUVs, they come with a wide spectrum of propulsion and actuation configurations, ranging from fully actuated degrees of freedom to a mix of actuated, underactuated, and coupled, decoupled degrees of freedom. One limitation because of such complex configurations and actuators is that they may not be, these traditional AUVs may not be optimally suited to the targeted application. Therefore, design of an AUV can benefit from having its propulsion system tailored to the target application. My today's talk is focused on floats, which represent a specialized class of surface and underwater vehicles deployed in different marine environments, and their mobility of different platforms ranging from passive drifting with ocean currents to active buoyancy controlled scaling, vertical scaling of deep water columns. These floats, they come with a variety of onboard sensing to autonomously monitor and collect essential data like conductivity, temperature, turbidity, depth, dissolved gas levels, etc. With wide applications in oceanography and climate science, like methane seeps exploration, harmful algal bloom tracking, subsurface current observation, biological monitoring, etc. Here you see an evolution of the float development of technology in floats from late 90s to the present day. And they were the initial league of floats. They were mainly referred to as Lagrangian floats. So why a Lagrangian float? Because it follows the Lagrangian framework of fluid dynamics. That is, the float moves passively along with the flow of water it is embedded in, rather than measuring properties at fixed spatial coordinates, which is typically referred to as Eulerian framework. The first generation of Lagrangian floats developed in the first float was developed in 1996. You can see how it comes with no actuation. It's a passive device. So then the mobility of the float is achieved using a drop dead weight at the bottom of the platform. So once deployed in water, you can see how it takes it all the way to the bottom of the seafloor. And when you release the drop weight, that's when it starts climbing up all the way to the surface. And in the due course, the onboard sensors gather measurements from the ambient environment. The second generation of floats, you can see there is a buoyancy control feature achieved using a piston mechanism. So which allows the bot to, or the float to go to specified depths and gather data. Later versions and more recent versions, you can see more advanced sensors like cameras that are mounted on the float, and also additional mechanisms like the external oil bladder, which is combined with the drop weight to achieve better control of along the vertical dimension. But one main observation in all these traditional floats is there is no active control of motion of the platform. In our work, we are specifically focused on the application of methane seeps exploration. Methane seeps are locations on the ocean floor where methane gas escapes from the reservoirs underneath the seabed into the ambient water, surrounding water. And study of methane seeps is significant in marine science because of the impact they cause, they have on different oceanic and atmospheric processes. For example, they affect the marine microbes that indeed consume methane, influencing the microbial ecosystem, and any methane emissions reaching the surface contribute to the methane levels in the atmosphere, in turn affecting the global climate. Current methane observation methods use deep towed side scan sonar, ROVs, underwater gliders, which are either expensive or have restricted mobility. And some of the requirements in the application, you can see how they impose the need for precise motion control in the vertical dimension while affording minimal to nominal motion demands in other horizontal dimensions. And also allowing for a systematic progression of prototyping iterations. The mobility platform that we initially designed, it was meant to operate at shallow depths, although we envision in the near future to do final deployment, which will be offshore along US Atlantic margin, which is approximately 90 miles east of where we live here. So the design that we came up with relied on a quadrotor based configuration with depth tracking capabilities. So as you can see on the figure in the right, the mechanical structure adopts a modular design combining a 3D printed bodies frame and a watertight enclosure to house the electronics. This was mainly done to, in fact, to decouple some of the waterproofing challenges we had in our earlier prototyping efforts, which I will show in the coming slides. In a sense, in contrast to the traditional floats, you can call this more like a hybrid float because it combines features of a Lagrangian float and a quadrotor type of platform. Which is achieved using 4 electric motor propeller-based thrusters that are aligned along the vertical heave axis. And it has a pressure sensor mounted on the float to obtain depth feedback. And combining all these eventually to do precise, accurate depth tracking using a PID controller that is implemented on board the float. Yes, as I was mentioning earlier, these were some of our previous design efforts in our lab to build an underwater platform. Although initially it was meant for three-dimensional motion, we rather simplified the control challenge to to just vertical dimension, and then the idea is to add one step complexity, add increasing complexity on the robot. As you can see, the structure was the body frame was a monolithic structure, which was 3D printed in-house. Although it achieved mobility after a few, maybe an hour or two, we found spoonful of water inside. And then even after several iterations, it was waterproofing was a big challenge. So then we moved toward a design which kind of decoupled that problem by designing the structure around the watertight enclosure. So these are some of the design details, and all these were designs were carried out by senior design undergraduate students as a part of a capstone project, while taking some minimal guidance in the design process. So these are some hardware details. So at the heart of the hardware is a Raspberry Pi, which is doing all the processing and implementing the PID controller, taking readings from the depth sensor and sending commands to all the thrusters through these ESC motor controllers. So these thrusters are brushless motors, so they need dedicated speed controllers. So and you can see a tether was going all the way. It had an onboard battery, but the sending the basic commands to the bot was through a tether. And a Simulink-based coding of the PID controller was achieved and downloaded onto the Raspberry Pi. So this kind of reduced the coding challenge for mechanical engineering students. I can go into more details later if someone, and this also allowed a real-time gathering of the data and also changing the PID parameters on the fly. In terms of testing environments, we initially did some basic mobility testing and also testing the waterproofing in a storage tank that we bought, just filled it with water and did some mobility testing. And then we took it to the deep water pool that we have at the university, did more rigorous testing. And then we also took it to an outdoor lake for some preliminary experiments. So we presented this work last year at the Oceans Conference, which is focused on all research related to oceans. So I'm going to play this video, which is like self-explanatory, and later maybe if I can touch upon certain things, certain gaps in the video.
I'm going to disable that now.
Okay.
Sitting out of the water.
As I was mentioning, these were our initial testing phase, where we had to achieve a balance between the CG and the center of buoyancy. So it had passive stability. And then just using one pressure sensor, we were able to do depth tracking. And that's the response to different step inputs and staircase inputs we were giving to the float. And one of the students was a scuba diving instructor, so that came in handy while doing these experiments. So as you can see, we were providing a sinusoidal reference of depth, and the float was tracking such a reference signal in real time. The current platform has capability to go up to like 100 meters below water. And one of the requirements is to stay on the bottom of the seafloor. So we tested some kind of mock, so it was resting on the floor for up to 15 to 20 minutes. And then we made it come resurface. And you can also see how we went after a symmetric design in order to enable modeling of the platform for controller development purposes. We had some challenges in the outdoor environment. Any small currents would drift the board horizontally. So there's a lot more work to do. And you can also see how it's not clear water, so it's difficult to see in the underwater environment. So then any vision-based sensing and control presents a challenge. So these are some data from the depth sensor and the tracking response to a step input, a staircase, and a sinusoidal reference, and some changes in the reference here, sinusoidal in terms of frequency and amplitude, I guess. As part of the ongoing work, we are currently working on extensions to the prototype to carry more hardware and also have the robot an ability to withstand ambient pressure at deeper underwater environments. Field tests at depths up to 500 meters are planned once the robot is equipped with the needed enclosure and pressure compensated sensors. We're also implementing a active postural control so we can achieve navigation in the horizontal plane. It's a lot bigger, so it can carry more battery size, a big sized battery and other hardware needed for different sensing applications. Currently, it doesn't have a methane measurement sensor, so that will need some modifications to the prototype. And so that's the future ahead. As part of a collaborative project, we were thinking about ideas for what we should implement. And one main challenge in underwater environments is localization. As we all know that underwater environment is a highly GPS denied environment. So localization of underwater sensor nodes is challenging. And hence we have to look for alternative methods. While the SLAM is very developed for terrestrial and aerial applications, underwater environments is still a big challenge. So one idea is to have a combination of heterogeneous network of nodes. For example, if you look at surface buoys that you see here, they are anchored to the bottom, so they stay where they are. And they're at the surface, so they have a GPS signal, so they can get localized. They have their location at a, they know their location at a very high accuracy. So now we can think of a combination, for example, mobile nodes like AUVs can be referred to as mobile nodes, which can use a dive and rise path planning algorithm in their motion, so they can rise to the surface, communicate with a reference node or a anchor node, localize themselves. And as they dive back into the waters, then they can propagate that location using dead reckoning until they again they drift away from, and the accuracy is now not good anymore. But you can also see how other randomly deployed nodes that may be passive, or it could be floats that I was just describing, could localize themselves by just measuring distances to such mobile nodes at different times, and using triangulation for the purpose of localization. And once the localization problem is solved, then I think as a network, they will be more useful for different ocean exploration tasks. In conclusions, today I presented floats as a specialized form of marine vehicle platforms for different oceanic observations, and presented development of one single robot system that is, it is ideal for methane seeps exploration because they need such vertical profiling. And then using a Simulink-based interface reduced the coding challenge and also enabled on-the-fly tuning of PID parameters. We conducted systematic experiments in water tank, deep water pool, and then an outdoor natural water body. And then ongoing work on implementing active control and the objective of achieving more deep underwater deployment. And I presented some future prospective future directions. Finally, I would like to acknowledge my collaborators. Kong Wei is a junior faculty, is recently joined assistant professor in our department. His focus is he specializes in marine robotics. And then Alexander Boshtansky is a professor in oceanography. So he has spent 20, 30 years in developing sensor payloads for methane detection, but they just manually let them in. So then this collaboration is about how about we just add some thrusters and maybe use buoyancy control to do more going to the depths, larger depths, and then achieving more local accurate control using thrusters. So that's the basic idea. And then Rob Stewart is a graduate student, and he was instrumental in leading the undergraduate teams. We had 2 teams over 2 years. All these are undergraduate students that me and Kong Wei advised in this project. Thank you. I'll be happy to take any questions if you have.
Yeah, thank you, Dr. Krishnanand, for that insightful presentation. We can take some questions from the audience.
Hello, Professor. Am I audible?
Yes. Yes, I can hear.
So my question is like what we see in the underwater robot, that it was tracking the jet reference using the pressure sensor. How about XY tracking, which could happen underneath? Let's say we incorporate IMU in that. Would that help in? Would that be sufficient itself, or would we need something more? As you said about surface buoys and all these concepts. So can you?
Yeah, that's a great question. Yes. So as you can see, the initial phase was just control in the vertical dimension. So a depth sensor was sufficient. And also all the thrusters, we just gave the same PWM signal to all of them, right? So either they go up or down the same, right? So they don't have horizontal mobility. In order to achieve that, you can use the differential capability. Have one diagonal of thrusters more speed than the others, then it'll pitch and start moving sideways. So now the IMUs, the gyro sensors in particular, will help in postural stability, right? So you can, because you're getting feedback of orientation. But then the horizontal mobility, right? So you can either use dead reckoning to integrate velocities. For example, you have IMU has linear accelerometers, correct? So you have to double integrate that to get displacement. So for, I guess you can get some displacement information, but they always have inaccuracies. So I think on the surface, you have to rely on GPS, correct? But for underwater, it's a challenge, yes. I don't know if I answered your question.
That answers. Just a follow-up, like the surface buoys.
Yeah, sure.
Itself.
Surface, yeah.
Yeah, those actually gives you feedback like the GPS, which does to the ground, right? Is that
Right.
a similarity in that?
I mean, surface buoys, they get directly GPS signal, right? So they localize themselves, right? Now we need to come, the bot has to come into the proximity of the to be able to establish a communication link with the reference node and localize itself, correct? But in the underwater environment, you don't have a GPS signal. So you have to depend on onboard sensors to propagate that positional data. Right.
Yes, okay. I got it. Thanks, Professor.
Any more?
Okay.
Hello. Am I audible?
Yes, it's breaking, but yeah, I can
so,
hear.
So my question is, how accurate of a model do you have of the robots that you have developed? So, and the follow-up question is, I mean, what is the PID tuning scheme that you have adopted?
Yeah, so how accurate is the model, you said, right?
Since you're using a PID controller, you need some...
Is it like how accurate?
Yes, I mean, there might be several coefficients underwater. Do you have...
Yeah, I mean, PID is a model-free control, right? So you don't have the need to use any model. So the initial, it was mainly trial and error, but also like, how KP, KI, KD, they have different responses, correct? They affect different aspects of the response. So then we were using such kind of knowledge to tune these parameters on the fly, because our goal was to achieve that depth tracking. But so initial problems were how there was a mismatch between, or there was a lot of distance between the center of gravity and center of buoyancy. So we had to like bring them closer. So then it could, it had like passive stability in the vertical dimension. So then that made the control problem simpler.
Okay, thanks a lot.
Okay, because of the time constraint, we can't take any more questions.
Yeah, we can. Yes, we can. Yeah, please reach out, and we can talk offline.
Okay, so this conclude this session. So once again, we'd like to thank Dr. Krishnanand for his presentation.
Yeah.
Thank you, Professor.